Hello everyone, welcome to the final session of DSF for 2022. Or maybe not, there might be another one in 6 months, who knows. So the main event, as it were. So I'd like to welcome Amrit Nandy. And he's here to talk about data science in the world of price and promotion. As part of the dunnhumby science team, Amrit works on new research problems in price and promotion capability. In his previous roles, he has worked as an applied data scientist supporting retailers on their P&P strategy. His other interests include panel management and measurement and retail setup.
Thank you, Tom.
Round of applause for Amrit, please.
Thank you. Thank you. Good afternoon, everybody. My name is Amritangsu Nandy. I am a data science manager in dunnhumby Global Science team. I work on research problems within the price and promotion capability. So today I'll try to share a quick background of dunnhumby's operation as a company, and then I'm going to talk about price optimization in grocery retail setup and dunnhumby's approach in solving this problem. I'll start with a small example to explain the problem, and then talk about the scale of the problem in a realistic scenario, and then talk some of the techniques that we use to solve these problems. And I'll finish with a high-level description of dunnhumby price optimization ecosystem, so to say, and some results from our previous implementations. So dunnhumby is a global customer data science company with presence in all continents, as you can see from the map, except probably Antarctica. We manage 770 million active customers through our 78 retail partners. We work with those retailers for different capabilities like price and promotion, category management, media, and customer knowledge. And we also work with global major CPG clients like Unilever, Procter & Gamble, Coca-Cola, etc. So let me explain the price optimization problem with a toy example. So let's say we are interested in a small grocery store who only stocks 5 items, an egg item, 2 different type of bread items, brand A bread, brand B bread, milk item, and then a carrot item. So the retailer might want to achieve different objectives with their store. Like they might want to maximize the profit from their store, or they might want to be known for the organic brand they stock in their store. I mean, our grocer is only interested in achieving financial objectives like maximizing revenue or cash sales, maximizing profit. In particular, for this example, we are talking about just maximizing the total number of units that they sell from the stores. Now, they can do multiple things to achieve their objective of maximizing the number of units that they are selling from the store. We'll be talking about one of the most obvious ones, which is by playing with the price of the products. So we as customer, when we purchase something, price is one of the key factors when you decide whether to purchase that product or how much to purchase. But that doesn't mean that the grocer can just make all the products free to maximize the number of units that are being sold from the store. They need to consider constantly. First of all, they need to recover the cost of the products that they are being sold from the store. And they also need to recover other costs, other operational costs. And not just about cost, there are other constraints or constraints that they need to consider before they set the price. So some of these constraints could be like, one of the bread type, brand A bread, has to be 50% cheaper compared to brand B bread. So it could be a different type of bread, different quality. So they're trying to manage that perception by pricing one of the bread cheaper compared to other brand of bread. For some reason, they don't want to be expensive. The egg product, they don't want to be more expensive compared to a competitor store. So that could be another constraint or rule that they want to set while they're thinking about setting the price. The vendor of the carrot might want the grocer to run the promotion on carrot for the next 3 weeks. And one of the most important thing is we usually when you go to a store, we see price like it's rounded to some number like 2.49 or 2.99. You don't usually see a price like 2.37 in a store. So these are the type of things that the grocer need to think about when they're setting the price in the store. And of course, there are many others. These are just some of the examples. And as you can see, even with this small example, considering these constraints, set up the price of the product, it's not a straightforward thing. You need to think of some algorithm to do that. It's not something very obvious that we can do. Now, let's talk about this problem in a slightly more realistic scenario and try to give you a sense of the scale of the problem. So many retailers around the world, they would stock around 50,000 products in their store. And they would operate in 10 different regions which are aligned to different price and promotion strategy in a market. So, which means that they need to think about setting 500,000 price points every week. And not just that, they need to think about like tens of thousands of constraints, something like we talked about before, similar to something like talked about before, while setting the price. And they also need to think about thousands of promotions that are already planned. So as it is, it's quite a complex problem. And usually, the users of price optimization software, they run multiple what-if scenarios before deciding on the final pricing strategy. So the software has to come up with the optimized price almost in near real time. It has to also be updated with the latest available week's data. So, like I said, it's quite a complex problem, but also the speed that we need to solve this problem is very important in the price optimization problem. So I'll try to explain our approach in solving this complex problem, again with some of the small examples in subsequent slides. So the first toy problem that we discussed, it can be summarized as you're seeing in the picture. So we are interested in optimizing some financial objectives. In our case, total number of units. We are trying to achieve this by playing with the price of the products. And there are some constraints that we need to think about while we are setting the price. Now, if we present the problem like this, you probably already have noticed that there is something big missing. We don't know how the total number of units change when you change the price of these products. So we need something to predict the total unit sales based on price and other variables, other related variables like promotions, time of the year, to attempt the optimization problem. So in next slide, we'll talk more about how can we predict the units. So it's probably not a bad approximation if we say that total number of units being sold from the store is also kind of the demand of the product in the store. I know that there are some things like out of stock and stuff, but then it's not a really bad approximation to talk about demand and units interchangeably. So we normally use these two terms interchangeably. So the total demand from the store is just the sum of unit sales of all products. So we can predict the demand of each product individually. Let's think of different types of variables that could influence the sales of a product. So product's own price is obviously one of the most important variables. And not just own price of a similar product would also influence the sales of another product. So in our previous example, let's think of what happens if we reduce the price of brand B. So if we reduce the price of brand B, it will not only help the brand B to get more sales, but it will also probably steal some of the sales from brand A. So some of the brand A bread buyers might now find brand B bread more attractive, and they might just switch from brand A bread to brand B bread. So of course, price of own product and price of similar product, we call them substitute products, they are important. Then usually products sell more when they are on promotion. Now there are different types of promotions that we consider. So what we call mechanic is just the communication of promotion. So whether a product is on 50% off or whether it's a buy one get one free type of promotions. So that's just the communication part when you talk about the mechanic. We have something called ad, which is just the leaflet, whether it's sent by post or some other way to the home. So that's what we call ad, and the display is just a prominent location in the store. So where we just put the products which are on offer. And then there are other temporal variables. If you think of a product like ice cream, it will sell differently in different seasons of the year. So seasonality is one of the key variables. Think about products which are sold a lot during holidays. So like Easter egg, mince pie, they would sell in like different quantities during the holidays. So of course, we need to know whether what are the holiday periods for that particular market, where you would expect to see some effect in the sales. And then there are trends which we also need to consider. For example, like a new launch product which would see a massive increase in sales in the first few probably months, which has nothing to do with price and promotion and other variables. So of course, we need to consider whether there is an organic trend in the pattern of sales of the product. So hopefully this will give you some idea about the type of variables that we consider while we try to predict the demand of a product. So let's talk about the characteristics that we need to think about when we are building these models. So the most important thing we need to think about why we are using these models for. Given that one of the use of these models are for price optimization, we need to think about the right causal drivers in the model, because we are going to push these models to some what-if scenarios that the model hasn't seen before. So we need to understand the right causal drivers, the proper cause and effect mechanism is built into the model from the outset. These demand models are also used for other strategy work, which I'll talk about more towards the end of my presentation. Now, this strategy work, they require us to understand how shoppers behave when you change the price of a product or when you put a product on a promotion. So that means that the parameters of the model has to be interpretable, because we are trying to predict something about a consumer behavior. So these conditions mean that we cannot use any sort of like black box model. So we need to, our model has to be backed by econometric theory. And that's what we do in dunnhumby. Our models are econometric based models. They reflect the natural relationship between price, promotions with the sales of product, and how shoppers respond to these economic influences. Now, there are choices in terms of what level we can fit the demand model. So I'll talk about some of those later. So one of the dimensions that I want to mention is the store dimension. So do we want to fit the model store dimension, or do we want to fit the model group of stores level? So some of this discussion, again, I'll take you through later. We fit these models as we have seen at product level, and also we fit the model at week level. We don't fit them at day level. Week is sort of a kind of optimum granularity in terms of time dimension. So basically, these models help us to predict the demand of a product at a particular group of stores and for a particular week. So far we have described the price optimization problem, explained why we need a demand model, what are the key variables in the demand model, what are the characteristics that we want to see in our demand model. Now let's talk a bit more about the different challenges that we face while fitting the demand model and the different techniques that we use in dunnhumby to overcome those challenges. So we're discussing about fitting model at product level, so which means that there will be hundreds of product hundreds and thousands of models that we need to fit automatically. And this model building process cannot fail because there is no manual supervision possible at that level. So, and it has to be fast. So the process itself has to take care of any different type of situations that it encounters kind of automatically. Unfortunately, there are different type of, like explaining here, different type of problems that we face while we fit the model. So the data can often be very limited. So for example, a product can only be in the market for a year or so. Now 1 year is not enough. time to kind of predict the seasonality of that product. There could be other things like we have limited signal in the data. So it could be that for a particular product, we haven't seen many price changes in the past. So which means that it's probably not enough data is there to explain the relationship between price and the sales of the product. We sometimes come across poor quality data. So for a particular segment of the business, there may not be enough good quality promotion data that is required to fit a good model. And one of the most relevant one in recent years is the unexpected change in sales. So during the early days of COVID-19 pandemic, we were seeing a lot of stockpiling behavior in the store, and which has nothing to do with price, promotion, trend, seasonality, other variables that we have in our model. So we need to understand these behaviors and need to kind of account for these behaviors while we are fitting these models. So the conclusion is that not only the model fitting process has to be automated and fast, it has to take care of these challenges, and it has to be robust to these challenges that we have mentioned above. So how do we build robust models? So we use different statistical machine learning techniques ranging from aggregation of the data to the Bayesian hierarchical model fitting to fit these models automatically. We use techniques like outlier removal, structural break detection, which will understand whether there is sudden change in volume in cells. We use different methods for handling low volume items, and of course we use techniques for seasonality estimation. So we'll take you through at least a few of these techniques in slightly more detail in subsequent slides. So this slide is about aggregation. So why do we aggregate our data? So we use these models for setting price of products, and retailers, they set the price of a product at price zone level. Now what is a price zone? Price zone is a group of stores where we expect the customers to behave similarly in response to any price change. So it makes sense to set the price at price zone level. And it also makes sense for us to build the model at that level. And this is something which we discussed when we were explaining the scale of the problem. When you're talking about those regions or format group of stores, this is what we meant by those group of stores or regions, basically. So those, and because we kind of fitting them at that level, so we aggregate the data from store level to the price zone level before we fit the demand model, and this gives us significant advantage in terms of having higher volume of data, which will result in a more stable model. These two charts hopefully explain this point well. In the first chart, we are just plotting the price and sales of a product for a single store. And as you can see that the sales data looks very noisy, and there is not much signal kind of coming out from this plot which will tell us between the relationship between price and sales. In the second chart, we are plotting the same price and sales, but not at store level, individual store level. We have aggregated data from 12 stores to a price zone level, and now we are plotting the sales and price trend at the price zone level, not at the individual store level. And now you can see that there is a clear trend emerging, there is a clear signal emerging between price and sales of the data. So no single store has a clear strong signal to it, but by the time we have aggregated the data at a price zone level across multiple stores, the signal is becoming to be apparent. This is a quick and relatively easy way of bringing the signal out. We have discussed the requirement for econometric demand model form. This is another technique which we use to fit the model for. So in our framework, we don't fit our models in isolation. We don't estimate our models in isolation. We use business structure to provide context. This is achieved through hierarchical Bayesian modeling framework. We use client data to generate the prior distribution for each model parameter for different products. But obviously, we cannot just use the data for the same product to come up with the prior distribution, because that will go against the fundamentals of Bayesian modeling. We use data from a group of similar products to come up with the prior distribution for a demand model of a product. So this first chart is a simplified example of different levels in the hierarchy we are discussing now. So again, let's say that we are estimating the model parameters for individual eggs, like brand AX to like some brand XX, and the prior distribution for all these models that are fitting at individual eggs level are coming from the total, like the egg level. So hopefully this will give you some idea about when we talk about the hierarchy, what are the different levels in the hierarchy. So we discussed about products with limited data and products with limited signal in the data. This framework helps us to use data from one product to guide the estimation of parameter in other products where we don't have enough signal in the data. So in the second chart, we are showing how Bayesian algorithm naturally balance evidence from different data levels. This is an example of distribution of prior and the likelihood, and then the final estimate, the final posterior distribution. So as you can see that the prior distribution is centered around minus 1.5. The likelihood is centered around minus 3.75. But the dispersion in the likelihood, which is shown by the green line, I don't know whether it's coming through or not, it's basically the second one from the left, is quite long, so which means that the dispersion is quite high. The data is really noisy, and the estimation is not very robust of likelihood. So when you look at the final estimate, which is when you look at from the posterior distribution, we can see that the mean of the posterior distribution is closer to the prior distribution. So this basically helps us to kind of balance the evidence that we see from the data and versus the prior that we have calculated at different level in the data. And the poorer, the sparser the product level data is, the more influence that comes from the prior. So hopefully it is evident from this picture. Now, again, I mean, the system, as we have seen, that there are different techniques that we use to solve this complex problem. So it's not just fitting the model independently for each product. We need to work with a framework which allows information sharing between different entities, automatically handling outlier structural break, seasonality estimates, etc. So this makes the parameter estimation process very complex. And as we have said before, in a typical retailer, we need to feed 500,000 models per week. Our brilliant scientific engineers implement these complex algorithms in multiple programming languages so that the whole parameter fitting process finishes within few hours, and which is why we can update our models every week with the new latest available data for the past week. And then our software is ready to be used for the next first working day of the next week. So we have talked about the demand model side of the price optimization problem. Let's revisit the actual price optimization problem. So by now we understand that, okay, so there is something that will help us to predict the whatever financial objective that we are trying to optimize, basically. So we wanted to optimize any financial objective for a group of products by varying the price of the products under some scenario and under some constraints. So for next part of the presentation, we'll restrict ourselves to a group of products we usually call category in retail term. And this is okay because there is not much interaction between products across different categories. So we can optimize each category individually and we'll still find an optimum solution. So for our discussion, I think we'll talk about profit as one of the financial objective. Now, how do we calculate profit? Profit is just if you take the revenue or cash sales and subtract the cost, that's how you get profit. Now, there could be multiple definitions of cost. We are not getting into those discussions. We are just assuming some fixed cost at product level. And then revenue is just if you multiply the price with the units of the product. That's how we end up with the revenue calculation. So again, our demand model will help us. Again, sorry, we'll talk about this example in a bit, and then I'll talk about how this optimization works. So here, let's say again, it's a very small example, probably very unrealistic example, but this is useful to explain the optimization problem. So we are talking about like two products in a category. So the price of one product is shown in this axis. I don't know whether the cursor is okay. So this axis, and the price of the other product is shown in this axis. And then the total profit of the category is shown by this gray shaded area. And the grid or this mesh type of thing, this is showing what are the constraints that we need to consider. So what we do, we start with the current price point of that we have seen in the latest week. So this green dot is basically showing what is the current price of these two products. And then we try to, through the optimization algorithm, through gradient descent or ascent, we try to find the local maxima around this point. So that's, so that's the optimization problem that we are trying to solve in this small example. Now, why we start with the current price? There are many different reasons, many different technical reasons, but one of the good reasons is that if we change price too much, of course, that will give customers, the customers will not be very happy. So that's why we start with something the customer has already seen in the latest week, and then try to find the local maxima around that point. In next section, I'll explain why we fit our demand model each week. So it helps to react to changes in product mix, competitive environment, macroeconomy, and new source of data. So this also allows us to get forecast based on recent weeks' data and to re-optimize to exploit changes in demand forecast. So with another toy example, we'll show the benefit of dynamic learning. As before, we are assuming we only have two products in the category, and again, they are shown by this two axes, the price of the products, and the profit chart is shown by this gray shaded area. And now this yellow dot is showing the current optimum point where you would achieve the maximum profit based on the price of these two products. If we move on, and let's say that after a few weeks, the profit curve changes, right? And if we were stuck with this particular point, which was derived from previous example, the price point it won't be optimum. So, it has probably moved to another point. So that's one of the reasons that we need to kind of update our model frequently and do it on a weekly basis in our case. So I think that's probably all of the technical discussions, the techniques that we use, and the challenges that we face in terms of fitting our models and in terms of optimizing. Now I'd like to talk about a bit more about Dunnhamby's price optimization framework at a very high level. So we discussed the mathematical optimization part so far, but then there is another part which is understanding how customers behave and what we call like strategy work, which balance the recommendation that we get from the mathematical optimization. So there are, like we're discussing, there are different rules that we need to consider. So this strategy work that we are now explaining, they help us to come up with those rules. And at the end, these two stream of work has to be kind of joined up. And basically, the rules help us to join these two stream of work. So it all starts, so this is kind of a description of the whole ecosystem, Dunnhamby price optimization ecosystem. So it all starts with the client's transactional data. It comes to Dunnhamby's solution, client data solution, and then we aggregate data, we fit our demand model, and then we optimize based on different objectives. So like we said, the objectives could be maximizing the volume, maximizing the sales, or it could be maximizing profit, etc. And then once we found the optimum point in terms of the price, we forecast our sales, revenue, profit based on those optimum points. It gets reviewed within the client's team. So it gets reviewed internally within the client, within the retailer's team, and then finally it gets implemented in the store. Customers see those prices, they do shopping based on those prices, and then obviously that get captured in the new transactional data in the future weeks. And then the whole circle starts again. So this is just one part of the story where we are talking about mainly the mathematical optimization part. Now, again, another part that we are just saying, it also starts from client data solution. And then we have different verticals within Nandy who work on customer knowledge and their customer segmentation, so which help us to come up with the strategy, and then this strategy gets translated to different rules, and then they get pushed to the optimization problem. So this is how finally these two different streams, they come together, and we end up with sensible pricing in the store. Now, this is just one example of the strategy work that we do. So when we are thinking about what should be the right price and promotion strategy for each product or each category, we try to think about two metrics: how important this product is for the customer, and also how responsive is the product to different economic influences like changing price or promotion. So we combine these two metrics, and based on these two matrices, we come up with different strategy for each product. So this is just one example of the strategy work that we need to do, and this helps us to kind of provide a guide rail to the final price that we send to the role, send to the store. So there's just one example I want to talk about. So if we are only focusing on the recommendations from the demand model, we would have seen that the bananas are usually very inelastic, which means that the retailers are tempted to change the price of bananas. And that happened in the past when the retailers have changed the price of the product, thinking that they are inelastic and the customers probably wouldn't react that much. But they are really important for the price perception, because that's the customers buy quite frequently and quite a lot. So, and that ended up having some negative press, and it's obviously not good for the price perception of the retailers. So hopefully that gives you some idea about why this strategy works. They are important, along with the purely mathematical optimization problem that we just talked about in the beginning. And finally, this is just some result that we have seen from our previous implementations. I think the numbers that we are seeing, and I think they're all from North America market, and you can see the variation in terms of different type of stores. So we are working with some retailer who has only 25 supermarket stores. We are also working with some other retailer in the other extreme, where they have like almost 400, close to 400 convenience stores in US Mid-Atlantic region. And those, at the last column, we are showing the different objectives that we are trying to achieve through our price optimization software for those retailers. And then usually we see, I think these are some of the top-end results that we have seen. So we are seeing that up to 8% of sales uplift and 5 to 10% of profit uplift for these retailers when they have implemented our price optimization software. Like I said, they are one of the best results that we have seen. Usually we see 2 to 3% of unit uplift and 1 to 2% of profit uplift whenever we implement our softwares quite regularly. So I think that's the end of my presentation. Thank you so much for listening. My name is Amritangsu Nandy. Feel free to ask me any questions, and then of course we will be available after this chat. So please come us and see us, the Nandy team. Thank you.
Round of applause. Okay, we have time for maybe one or two questions before we wrap up.
Yes, please. Yeah, please. Do you want me to?
No, I can do it if you want, but yeah.
Yeah, please, if you could.
Yeah, okay. So bearing in mind sort of increasing inflation in a lot of countries is quite big, I was curious what kind of new features you're considering bringing into model to account for the potential.
Of course. of course. I think it's a very relevant question. We are getting these questions quite frequently, like you mentioned, from our partners, retailer partners. I think we already have something in our model which account for this, these situations. So for example, the trend that we talked about, it basically, the trend variable itself has nothing to do with the price and promotion, but it helps us to capture any organic growth or decline that we see in sales. So that's just one example. Then there are other features and other techniques that we use which kind of automatically account for this type of scenario that we are seeing now. Hopefully that answers. Thank you.
Gentleman in the orange shirt. John?
Yeah. So you mentioned about that uplift numbers on units and profit.
Sure.
I was curious, how do you measure that?
Yeah, of course. So we have kind of two broad ways of measuring that. One of the ways doing a proper test versus control type of measurement, where we implement our strategy to a group of stores, and then of course we find similar stores where we don't implement, and then at the end of the exercise we try to compare between test and control, of course. And also, I think the other thing is that if we are confident about the forecast that we are doing with the help of the demand models, then we can calculate different scenarios. And basically, we can calculate a scenario where with the retailer's current strategy, we can calculate another scenario based on what we are recommending. So that, again, you can take the difference, and this will give you some idea. Of course, the preferred one is to do a proper test control type of scenario, but it's not always possible to do that. In absence of that, the second one is what we do.
You talked about substitution there in the price.
Sure.
Prices. Can you infer anything about brand strength from that and the stickiness of a brand and people moving away from that brand?
I think in this case, because we are restricted within the price and promotion capability, the question that you're asking, again, it's a relevant question, and we try to answer that question probably in another capability. Probably category management is the most appropriate one for that sort of answering that sort of question. But just for this particular example, price optimization problem, we normally don't look at stickiness and the brand basically loyalty. But then, of course, we have other verticals within Nandy who look at brand loyalty and stickiness, those sort of stuff. We definitely have different metrics which measures this, mainly brand loyalty.
Yes, so you mentioned that for you it's really important to identify the causal drivers.
Yeah.
How do you make sure you do this and not pick up, like, for example, spurious correlations?
Sure. I think that's why we use the econometric demand model, because that has a strong history of research. And so I think, again, very good question, because we couldn't just pick any other model. We need something which is backed by this strong econometric theory. So hopefully that helps us to kind of identify the right causal drivers in the model.
Thank you for sharing. Actually, inspired by your banana, like
Sure.
inelastic nature.
Sure.
Are there any kind of ethic considerations that you guys would implement when doing that for your clients?
Sure. Usually these rules. So if there is any consideration which are coming from like business expertise, or which are coming from outside of the realm of the pure mathematical optimization problem that you're talking about, they usually come through the rules that we set. So let's say that if you don't want to increase the price of certain necessary products, you can set that rules that the price of this product should be limited or should be less than this number. And that will, while you are doing the optimization problem, that will ensure that you don't end up having a increased price of those products. So I cannot talk about, like as a scientist, I cannot talk about what are the different kind of consideration that we need to make. They normally come from the people who are working with the clients. But once they decide that, they just translate that to rules. And once the rules are in place, hopefully the mathematical optimization does a good job of making sure that the price is within that bound. Thank you.
Last call for any questions?
Yeah, on the data, I think at one point you said we trade like 500,000 bottles a
Yeah.
week.
Yeah.
And across a long period, over a year,
Yeah.
a lot of prices, a lot of data. Just how do you manage that in terms of? And you said it took a couple of hours to train.
Few hours probably, not a couple of hours. Yes, for some retailers it is done within a couple of hours. But yeah, I would say it probably like more, in a very complex, if for a big retailer, it's not more than like overnight job. For this type of work, like I said, we have a brilliant data science engineering team who work along with us, who are part of the same price and promotion science team. And over many years, they have built like many different C++ libraries. So basically, probably the short answer is that we feed those models using our own, or coding our own algorithm. It's not just that we take any off-the-shelf package for like from Python or some other language. Of course, we need to build our own code base to do that. And that's, of course, once you have that flexibility, you can parallelize or you can work which will work in your favor. Yeah. Cool. Thank you.
A round of applause for Amit. Thank you.
Thank you. Thank you. Thank you.